Welcome back. Let's do a node voltage with a power balance. Now this is a very interesting problem with lots of really cool things happening. Lots of neat little tricks. This is like the hardest node voltage problem in the chapter. Although we're going to keep using node voltage throughout the rest of the semester. It's a pretty fundamental technique. Okay, this is what we got. We have a independent device and a dependent device. This one's a current source and this one's a voltage source. And this guy, right off the bat, this guy is given by 84I delta. So we need an I delta somewhere. And I delta is right here. This is I delta. So there's a current through here, through this resistor. It's being measured, and then that information is being sent over to this device somehow. Magic, probably wires that aren't shown. Could be infrared, could be radio waves. Anyway, this thing is being measured, and that information is sent over here. And this guy puts out 84 times whatever I delta is. All right, and it could be a source, it could be a load, and this one could be a source and could be a load, but at least one of these is a source. All right, let's put in the values that are on here. This is 40 ohms, this is 160 ohms, this is 10 ohms, this is 20 ohms, this is 8 ohms. And it's a node voltage problem, so the ground node is always down here on these the problems we're going to do. This is 25 amps. That's what's given. This stuff. Okay, we're asked to find we're just asked to do a power balance using node voltage. Well, you do node voltage first, so use node voltage. Because that's what we're trying to learn is node voltage, but we want to find a power balance. That is, we're going to find the power in every one of these devices and make sure that they sum up to zero to obey the law of conservation of energy. Let's label these nodes. There's one up here, right? If you start with 0, which is all the way across the bottom, 0, and you go up and the other side is 0, these three items are all on the other side of 0. So this is V1, this is also V1, right? So that, just check each item. You go up, start at 0, you go up, you're on the other side, there's a node. You go up on this one and the other side, there's a node. Happens to be the same one. Same thing over here. You go across, there's another node. So and then here you go across, it's a different node. So this is V2. Okay, what about this node? Well, you could label it V3, and that would be okay, but we happen to know what it is in terms of this voltage device, this voltage source or load. But anyway, if it's 0 volts down here and this guy is adding 84 I delta volts, then this is 84 I delta volts. So look, don't get confused. This is I delta, which is a current, but this is a voltage source. So it's turning, there's a conversion factor in there, if you want to think about it that way, that's turning whatever is measured in amps, it's putting out a corresponding amount of volts. All right, so try not to get confused on that. So let's solve the node voltage stuff and just see what we get. So in node voltage, we're summing currents into nodes, so we need to come up with some current directions, right? So we've got 25 amps coming up, so we'll stick with that arrow direction. Let's say that splits and some comes down here, and then some comes out of the other side of node V1, and we've got I delta coming down. We've got to guess the current direction coming out of V1 on this side. We got to guess, and vote now. What do you think? What should we do? Well, it's very much for me a guess, but let's guess this direction. And we got to guess a couple of more times. Like here, we got to guess. There's a current coming out of this. We like to imagine currents coming out of the positive terminals, so we'll guess this current direction coming out of the positive terminal going around this way. Okay. Then here, if these two are coming in, you know, we'll guess that way. But you know, some of these guesses are better than others, but probably at least one of them's wrong, and so we'll just get a negative number on the current. Anyway, let's write the NV equation. So node voltage 1. So I like to write in as negative and out as positive, just so I don't forget. And what do I got here? I've got 25 volts coming in, so that's negative. And then I've got this current right here is coming out, so it's positive, and the potential difference is V1. V1 minus 0, which is just V1. Okay, over 40. And then this, let's do this current, this one here. So this one's coming out, and it's going to be V1 minus V2, the potential between these two nodes over the resistance 10, and it's coming out, so it's plus. And then I've got I delta coming out here. So I could just write minus I delta, or rather I could just write plus I delta because it's coming out. Or I'm totally on the wrong track, aren't I? Somehow I jumped over to V2 node. I confused myself. Did I confuse you? I hope not. I hope you're paying attention better than I am. No, we're here at I delta. What's going on? Let me back up. So I've got 25 amps coming in, it's negative. I've got V1 over 40 amps coming out, that's positive. And then here I've got V1 minus V2 over 10 amps coming out, so it's positive. And then here I've got, I delta coming out, so that would be positive. So yeah, you could write positive I delta equals 0. You could do that, and that would work. But let me put it in terms of these voltages, because that's what I've been doing so far. All right, just to show you there's different ways to do it. So it's going to be positive coming out V1 over 160. So basically what I'm saying is I delta is V1 over 160. It's kind of what I'm saying. I'm just using that here. Different ways that you could do it. I'm doing this for a reason. I'm setting it up this way for kind of a reason, kinda. All right, let's write node voltage 2. So that's this guy right here. So I've got the same term coming in, but so it's in, it's negative, but it's the same term right here, V1 minus V2 over 10. That's this current right here coming into node V1. And okay, and then I've got let's do this one. I've got this guy coming out of V2 coming down. That's V2 over 20, and that's coming out, so it's positive. And okay, now this term is coming. This current is coming into the node V2, so it's in, it's negative. And let's express it in terms of voltages. Okay, so in order for the current to be going to the left, this voltage here, this 84 I delta voltage, must be bigger than V2. So I write 84 I delta minus V2. That's the potential difference through 8 ohms. It gives me the current here. All right, and that's the 3 currents going into V2. Right? I've got this one, that's there. Got this one coming out, it's there. I've got this one coming in, it's there. Those sum to 0. Okay, so the reason I wrote them that way is so that we can count up the equations and the unknowns. Well, enough said on that. So there are lots of ways you can write it. But look, we have 2 equations. How many unknowns? We've got V1, V2, V1, V2, and we've got I delta, so we've got 3 unknowns. Now, if I would have, this term right here, if I would have used I delta, I'd still have 3 unknowns. So I need one more. I need one more equation, and I have it. It's this one. So I delta equals V1 over 160. So if you consider these guys as a system of 3 EQs, there's 3 unknowns, then there's a solution in here, right? So V1, V2, and I delta. So you could put this in standard form. Now you could eliminate I delta by just putting this V1 in here, and then you'd have 2 equations, 2 unknowns. You know, that would work. You could totally do that if you want. That's fine. But just to show you that another way to do it, that's maybe a little more mechanical, is just rearrange these guys here. So I've got NV1, NV2, NV3. Well, it's not in this third. This is just number 3. It's equation 3. Okay, 3. So rearranging this guy and putting it in standard form, I'm going to factor out V1 and I'm going to factor out V2. So I'm going to get V1 and a bunch of constants. It's going to be 1 over 40 plus 1 over 160 plus 1 over 10, just factoring out the 40, the 160, and the 10. And then I get V2 and this minus 110. And do this. So you do I delta with 0 and 25, just so that you have V1, V2, I delta standard form, right? This is how you handle this kind of thing, so you can put it in your calculator. Well, some calculators will take it like this. Other calculators need it standard form, and still other calculators use a matrix. But I'm going to just put it in this equation form. So rearranging this guy, you're going to get V1. You're going to factor out the minus 1/10, and then you're going to get V2, and you're going to factor out you know, all of these things, and you're going to get 1/10 plus 1/20 plus 1/8 plus, and then I delta has this 84 over 8 thing negative, so it's going to be I delta minus 84 over 8 equals 0. Okay, that's putting that into standard form, right? Factoring out junk and rearranging things. And if you need to use more steps, if it's been a while since you've had algebra, well, you do get faster at this kind of algebraic manipulations just by doing them. Anyway, this last equation here is going to look like, it's going to look like this when you put it in standard form. This is going to be V1 minus 1 over 160 plus V2 0, okay, plus I delta 1 equals 0. So, okay, this is just standard form for some machines, you know, your calculator or you know, whatever you need to do. And the solution that's going to get printed out or, you know, spit out by your machine is going to be V1 is going to be 352 volts, and V2 is going to be 212 volts, and I delta is going to be 2.2 amps. Okay, so if you need to manipulate this more to get it into your machine, your calculator, or your program that you found on the web, or whatever you're using to solve this system of simultaneous equations, you know, that's fine, do that. I'd like to see it at least in this form, please, because this is something I can grade, right? This here can be written in many different ways, but if you write them out like this, I can check them much easier and see if they're okay. All right, it's time to do a power balance. Are you ready? Are you excited about it? Hey, before we go on, let's look at these numbers and see if there's anything weird about them. V1 is 352. It doesn't sound too crazy given these resistor values. It's not like 3000 or 3. And 212 is not too bad. This is 2.2 amps. It's reasonable. And this is 25 amps. Nothing's totally crazy. And they're all positive, right? They're all positive, which means, well, especially for the current, it means that we guessed right on this I delta. Although, I think that was given. I delta was given arrow direction. Anyway, just as sort of a check before we kind of go on any further, let's do the power balance now. So power balance. Like those energy bars. That's where that comes from, power balance, I think. So let's just kind of proceed. Well, look, we've got P equals IV. We could use that. If we have the I and the V, we could use that. We could also use P equals I squared R. If we happen to have I and R, or we could use P equals V squared over R if we happen to have the V. Let's just see what we got. Let's do this one. So the power in the 25 amp device, let's use VI. Yeah, for those kind of devices you have to use VI. It's the only one that'll work because there's no resistor. So this guy is going to be, well, V is V1. The voltage across this 25 amp resistor is V1, which is 352. So it's 352 times 25. So this ends up being 8,800 watts in the current direction. So it's 0 volts on the bottom. That's less than 352 volts on the top. So really the sign is like this, rising from 0 to 352. So this sign, this arrangement right here is developed. So that means there's power coming from the universe, you know, coming from outside the circuit into this circuit. And all these other guys, these resistors are all leaving, power's leaving the circuit, right, as heat. This one we don't know yet, but we know now that the power's coming into at least this device. So yeah. That's an answer. Let's put it in a box so we can find it later, because we're doing a power balance, right? Then what do you want to do? Let's do the power in this guy, the diamond. Power in the diamond. So we could use VI, and where V is 84I delta, okay, and I is, well, I is this thing that it's this expression, right? I is the difference in voltage over the resistance. That's what we have for I. So I is 84I delta minus V2 over 8, right? So, you know, let's solve this one first. So this is 84, and we know I delta, right? Don't we somewhere? Yeah, here it is. 2.2. Yeah. Minus 212. This guy right here, and that's all over 8. And this is so minus, works out to minus 3.4 amps. So we guessed wrong. This current is actually, you know, physically going the other direction. So we stick with the arrow because we're already in too deep to be flipping arrows around. So stick with the arrow direction and just use the value there. It'll work out, you'll see. So what now? We got to do the V thing, right? So we could make a squiggle. So this is 84 and 2.2, which is 185. So now we can do this thing. So now this is 185 times minus 3.4, right? Which is minus 628 watts. And what about the arrows and junk? So I've got an arrow direction, and you could redraw the arrow if you want, like right here, right? So it's coming in at a negative and coming out at a positive. So it's coming in at a low energy state and coming out at a higher energy state. So energy is being added to this by this sign convention. We have energy being added by the sign convention, but the value is negative, so we got to flip that. So let me see it. This means developed, but it's negative 628 developed. So you could say that that's positive 628 absorbed. So it's a load. All right. So there's just, you know, it's because the current's backwards. Okay, the current's backwards. If we would have guessed the current direction at the beginning, if we would have guessed it the other way around, we would have got a positive value, and then this convention would show absorbed instead of developed, and it all works out the same in the end. So it's just inherently a little bit confusing. And you could rework it again if you want. So yeah, so we've got one source, 8800 watts, and we've got one load. This diamond is a load. We know that the resistors are all loads. So this guy, this 8800 watts, this circle right here is supplying power to the rest of the entire thing right here. Okay, do the resistors. These were the I don't know. These are the circles in the diamonds, basically. Now let's do the resistors. So where are we? Let's pick a resistor, any resistor. Pick one. Let's do the 40. Where's the 40? There it is. So we could use. We have V. Let's just use that. We have the V because it's 0 volts down here. So V is the voltage across S, and so we could use V squared over R. That's the easiest one to use. So this is going to be V1, it's 352 squared over 40 ohms. It's going to be 3097 watts, and of course it's absorbed because it's a resistor. Let's do the 160 ohm. And there we could use also 352 squared over 160. And there you end up with 774 watts absorbed. Let's do V2 is the next, or the 20. That's the easiest one to do right now because it's the voltage V2 is 212 volts squared over 20. That's going to give you 2247 watts absorbed. Then we could do, what do you want to do? Let's do this one. Let's do the power in the 10 ohm resistor K. So now here we need to use the potential difference, which is what we were doing over here. We were using V1 minus 0. Okay, but here we're going to use V1 minus V2. Okay. So that's V1 is 352, so it's going to be it's going to be 352 minus this one. It's the potential difference squared over the resistance, which is what the others were. It's just 0. The others were 0 on the bottom. Okay, and this so look, I'm using the high voltage over here minus the low voltage. Doesn't really matter, I mean, because we're squaring it, right? It's gonna, if it was a negative value, if we flip these around, it would be a negative value, and we're squaring it, so it doesn't really matter. Which is just an interesting thing having to do with power. But anyway, what's the answer? This is 1960 watts absorbed. The last one is the 8 ohm. That's the hardest one. The power in the 8 ohm. Okay, so let's use 84 I delta volts minus 212. So it's going to be 84 I delta, and I delta is 2.2. That's the voltage at this point minus the voltage at this point, which is 212 over the 8 ohm resistor. This quantity's square because we're using V squared over R. And that ends up to be 92.48 watts absorbed. And so if you summed all of these guys, so the powers, so you'd have 8,800 watts. This one source should add up to all of these other doohickeys, and those would be 628 plus 3097 plus 774 plus 2247 plus 1960 plus 93 And yeah, they do add up if you check that out, if you ask your calculator. All right. See ya.